And in Lecture 7, I'm going to go into the interpretation of mass spectrometry, starting with some of the original photographic images of mass spectra and how they were interpreted and used to discover isotopes, and then go to the more modern approach, which actually gives a mass spectrum with a histogram-like representation of the relative abundance of each mass-to-charge ratio. So mass spectrometers were originally used to discover isotopes and to precisely determine the masses of atoms. Again, recall quantitative analysis and how the atomic weight scale was determined based on gasometry experiments, the relative densities of vapors, and from that established the mole concept and use the mole concept to convert macroscopic weights to the weights, the masses of the individual particles. So this is something a little bit more direct and going to the atomic scale. So we saw in the previous lecture that if you bombard atoms, molecules with ballistic particles, namely electrons, you can knock electrons off the atoms and molecules, create a cation, and the cation accelerated and weighed, in effect, the same way the electron was weighed, namely by deflection in a field, magnetic or electric. Since there's limited amount of control to the bombardment with the ballistic particles, you get a tendency to get multiple ions. So you would expect to get, for a given atom of mass m, multiple particles of m to z ratio. So you get a +1 cation, you get a +2 cation, a +3 cation, as many as electrons there are, until you completely strip the nucleus of electrons. And so you would expect to see a converging series in the mass spectrum. In other words, you would expect to see something that looks like this, where on the right you would have the +1 cation, and you'd start moving towards the left, increasing the number of stripped electrons. So you get something that looks like actually a Balmer series type line spectrum. This kind of ticks off Domino because Domino knows that ionization potential increases with the number of electrons removed. So the second electron is harder to move than the first electron. The third electron is even more difficult to remove. And by the time you get to 5 or 6, forget it. It's not going to happen. So it becomes increasingly difficult to remove electrons. And so you don't really expect to see these guys. You probably are going to see +1 and +2 only for atoms. Some of the larger atoms, you probably get +3, like the transition metals. This does become problematic in protein mass spectra, which we'll just touch on briefly at the end of these lectures on mass spec. But if you think of proteins or a polymer with lots of protons attached to it, all those things can come off. So you're going to get all sorts of crazy things in the mass spectrum of polymers. So in the previous slide, I showed a mass spectrum that looked a little bit like a line spectrum from, say, an arc. So the UV visible, the Balmer series, for example. And there was a similarity in terms of the way the mass spectrograph determined or measured the spectrum. So this is the Aston mass spectrograph, and the way the mass spectra appeared is you get these parabolas of deflection for each of the mass to charge ratios. And on the right hand side, the exit port of the analyzer, namely the magnet, you would have a photographic plate which would essentially get exposed where the ions were crashing into the silver emulsion. And so the spectra would be an exposed piece of film, and they would look something like this, which is kind of taken from an Aston paper. So you have these lines or spots that appear on the film, and since you know the geometry of the camera, so to speak, namely the mass spec analyzer, you can determine the radius of curvature of the path, the parabola, and use mathematics to determine the mass to charge ratio based on the electromagnetic theory. In lecture 6, I've described the first of the mass spectrometry-like things as that cathode ray tube which bombarded atoms, turned them into cations, and drew them through the electrode to analyze in the opposite direction. The fancy name for this apparatus was called canal rays. So the modified cathode ray tube examined canal rays, which are the positively charged ions. And an apparatus, the same sort of type detection was done with the canal rays, namely a photographic exposure. And there were hints of multiple spots suggesting the existence of isotopes. One of the more prominent ones, the ones easiest to see, was neon. There seemed to be 2 spots in J.J. Thomson's experiments. So Aston was trying to improve upon this. There were really no definitive proof of isotopes until around 1910. And the way they were trying to prove the existence of the isotopes was via classic fractional distillation. So the types of things you do in organic chemistry when you try to separate mixtures of solvents, they were trying with mixtures of gases of different weights. It's extremely tedious work. Their almost heroic measures did get suggestions of the existence of the isotopes, but you want something a little bit better. So Aston creates the mass spectrograph, and his the schematic diagram is on the previous slides, but architecturally, in terms of the device itself, the construction resembles what I illustrated in lecture 6, part 4, or 3, whatever. 4 according to this slide. Anyway, so Aston has this device built, and he actually starts to see the spots. Now he needs a standard. So hydrogen is so small it just flies off. You can't really use it as a reference in the mass spectrometer in Aston's instrument. So he uses oxygen. So the beam, the electrons like destroy everything. You mangle everything in the spectrometer. So if you create a standard, essentially an internal standard of carbon dioxide and methane, you get a bunch of broken elements and what are called radicals, parts of molecules. So the mixture of carbon dioxide and methane gives you carbon and all the, I guess, variations of carbon and hydrogen leading and oxygen. So you get masses 12, 13, 14, 15, 16. And this is how oxygen becomes the atomic mass standard as opposed to hydrogen, which was used in the gasometry experiments. So Aston runs neon through his little mass spectrometer, and he sees 2 intense spots at 20 and 22, mass to charge ratio, and he sees some faint spots at 10 and 11. And these faint spots suggest that indeed the 20 and 22 are isotopes of neon, and they carry the +1 charge. The 10 and 11 are the +2 charge versions of those 2 isotopes. So far, so good. So he has the first evidence of isotopes. So Aston begins a systematic study of the elements and the attempt to discover the isotopes. So he includes chlorine in the study, and he notes in the case of chlorine that he gets a number of spots, and 2 intense spots at 35 and 37, and then their echo. So he decides that probably the principal isotopes are 35 and 37, based upon the faint spots that he sees at 17.5 and 18.5, which would correspond to the +2 cations of the 35 and the 37, which would be the +1. So he argues in the interpretation of the mass spectrum that the elemental isotopes of 35 and 37, so that would be the +1 charge, the +2 charge version of those same isotopes, same weights, would be the 17.5 and the 18.5. And then he has evidence for chemistry taking place. So the 36 and the 38, since he has that crazy concoction in the mass spectrometer as a reference, he's getting recombination in the beam. So he makes HCl, giving him a 36 and 38 line. Faint, right? Not much chemistry is taking place, but some is. And then similarly, which I don't have on the mass spectrum of the slide, is the 63 and 65 faint lines, which correspond to a different type of chemistry where you have a kind of carbon, oxygen, and chlorine molecule formed. Argon is heavy, and it's also good for looking at the mass spectrum in the case of Aston's spectrometer. So he sees an intense line at 40. He also gets a weaker line, less intense, at 20, so that is probably the +2 ion. And he also sees a weak line at 36. So at the time, the atomic weight determined gasometrically of argon was 39.88. That was the best practice determination of the apparent atomic weight of argon. So he estimates that the intensity of the MZ36 line is 3% based on the fitting of the equation indicated below. So if you take 3% of 36 and combine that with 97% of 40, you get 39.88, which was the experimentally determined atomic weight of argon in general from gasometry at the time. We're going to refine that, and you'll see that based on the refinement that the 3% relative intensity was not determined by optical density, it was actually just determined mathematically. The modern mass spectrometers use an electrode. A fancy name for it is the Faraday cup, which acts as basically a catcher's mitt for the ions as they come through the analyzer. And as they strike the Faraday cup, the ions generate a current. The current can be measured directly as a flux, namely coulombs per second, or you can use what's called a counter circuit to actually count the number of hits as they come in, so as a train of pulses. Either way, you can now take the information in terms of the intensity of the beam and use that to create a spectrum, much in the same way as you would create an absorption spectrum. So whereas you would have spots of different intensity on a photographic plate, now you would have a hard quantitative number. And the mass spectrum can thereby be presented to you as the mass to charge ratio on the x-axis and an abundance value on the y-axis, which would correspond to, say, same type of idea as an absorption spectrum or an emission spectrum in optical spectroscopy. So let's go back to the argon mass spectrum using a modern instrument. And this is sort of what you would see depending on how sensitive your instrument was. The version represented here is typical of a conventional analytical mass spec. So we get the major peak at mass to charge ratio of 40. The computer in the instrument will automatically set that to 100% abundance. It's a normalizing technique. So everything is going to be measured relative to the largest peak in the spectrum. In the cartoon diagram that I had at the end of lecture 6, I had the ionization process being achieved by bombardment of electrons. So by controlling the intensity and the strength and the velocity of the electrons, you can minimize the amount of destruction to the target atom or molecule. In other words, a clean mass spectrum contains only the +1 ions. You would try to minimize the amount of +2, +3s, etc. to avoid confusing the spectrum. You don't want too much information if it isn't necessary. So this is the type of spectrum you would see if you manage to control the electron beam, creating only positively charged atomic ions. Okay, so the computer has essentially scaled up the biggest peak and set it to 100. You see the isotope line for 36, and you'll notice it's not 3%, but actually 0.3%, and that's the true abundance of the argon-36 isotope. Again, this is determined experimentally as opposed to the 3%, which was determined mathematically by Aston. So Aston reported 3% using that formula. If you take the new data, you calculate that you get 39.98, which is actually a better figure even by gasometric standards of today or other techniques to get the average atomic weight of argon. So let's look at neon with a mass spectrometer. So recall Aston's experimental mass spectrum. He had two lines. Roughly, from his perspective, they looked about the same intensity at 20 and 22, and then he got a weak line at 10 and 11. Here, with the modern mass spectrometer capable of actually doing counting and determining the relative abundance, we see again the two lines that Aston saw, but in comparison, we now have the relative intensities taken or shown, directly demonstrated. So the computer records the data and processes it, takes the biggest peak in the spectrum. We're going to see this in all of the mass spectrum we encounter from here on in. The biggest peak in the spectrum is assigned to a value of 100. And every other peak in the spectrum is going to be scaled relative to that peak. So you'll see in this particular example that the 22 peak has a relative abundance of about 10% relative to the peak at 20. In addition, there is a tiny little peak at 21, indicative of a neon 21 isotope, and this value of 0.27% is roughly the sensitivity limit of an analytical spectrometer. You can get much more sensitive mass spectrometers for specialized isotope research, but in the typical analytical laboratory, the lower limit is 0.2%, which is about where you would find a peak in oxygen that's necessary, but we'll talk about that shortly. So we have the scaling taking place, and I want to introduce a little bit of jargon here. So the first bit of jargon is, what do we call the intense peak, namely the lowest of the isotope peaks with a charge of +1? And we call this the A peak. It is assigned to the lowest M to Z peak for a +1 ion. The other peaks are going to become the satellites. And in this particular case, the satellite line, the isotopic satellite line at 22 is designated as the A+2 line. The line at 21 would be the A+1 line. Since this has a second isotope that's prominent at the A+2 position, this would be considered an A+2 element. Okay, we look at carbon now, and we see the following pattern. We see the most abundant line at mass to charge ratio of 12. We see a isotope satellite line at 13. And since we've assigned or determined that we're going to call the principal ion A, the isotope line at 13 is an A+1 line, and this would be considered an A+1 type of element. From the relative abundance of these two lines, we can estimate, actually if you have a good enough mass spectrometer, you can determine fairly precisely that the isotopic abundance of carbon-12 is 98.8. The isotopic abundance of carbon-13 is 1.1%. Carbon-14 is unstable, and you would have to use a special mass spectrometer to determine it, but that would be the balance. This is going to become important now. So if I look at the calculation there below the isotopic abundance, I see that the relative abundance of C13 to C12 is roughly 1.1%. We're going to use that 1.1% eventually to count the number of carbons in a multinuclear or polyatomic molecule. So keep in mind that little calculation there on the left. We'll come back to it probably in part 2 of this lecture. We now look at oxygen. We see the most abundant peak is at MZ16. We see a small peak with a relative abundance of 0.2% at MZ18. We don't see the oxygen 17 in this particular case. So since the principal isotope satellite line is at 18, 2 units away from the most abundant at 16, this is an A+2 element as well. And again, we're going to use that 0.2% as a means to estimate the number of oxygens in a molecule. Nitrogen now should be recognizable to you as an A+1 element. Its isotope satellite line appears at MZ15. The most abundant isotope occurs at MZ14. Relative abundance is 0.4 to 99.6. And again, you can do the calculation there. And finally, we'll take a look at chlorine. So chlorine, again, in the modern mass spectrometer, is shown to be about 76% chlorine 35, combined with about 24% chlorine 37. And you have a trace amount of chlorine 36, which is invisible to most analytical mass spectrometers. So you would recognize this as an A+2 element. So we've looked at a couple of atomic mass spectra. What I want to do in part 2 is use the isotopic satellite lines as a means to count the number of atomic nuclei of a given type in a molecule. We're going to restrict ourselves to molecules containing carbon, nitrogen, hydrogen, and oxygen to keep things simple for this course. And here's some bibliographic references to the early days of mass spectrometry, including, and I've also added a modern textbook on the interpretation of mass spec where you'll find some of this material.